Here we have an example problem where we have a solid sphere is released from rest on a ramp that is inclined at an angle of 25 degrees. We want to find the acceleration of the sphere's center of mass as it rolls down the ramp, and we want to find the coefficient of friction required for the sphere to roll without slipping. Here's one of our keywords that we are looking for here. If we are talking about a coefficient of friction, that is related to force. We're trying to find acceleration, which is also related to force. And so we should be thinking of Newton's second law, F equals ma. But since we have a sphere here, we're talking about rolling without slipping. We also need to be considering the torque aspect. And so we're going to follow the steps that we've laid out for dealing with rotational dynamics, where we have both forces and torques acting on an object. Number one, we're going to start by drawing a picture, which is what we've done here. Step two is to find an object of interest. In this case, it's going to be the sphere. The sphere is the thing that's moving, so that's what we're interested in. We know that the sphere is going to be rotating if it's rolling without slipping, and so its axis of rotation is going to be here at the center of the sphere. The next step is a little bit trickier. We have to do force identification, but because we are talking about rotational dynamics, we have an extended object here. We're going to do force identification like we've done before, but we have to be aware of not just what forces are acting, but where those forces are acting. So what we're going to do is draw a circle around our object. And look for points of contact. We have a point of contact with the surface there. And so we know we have a normal force. That normal force is going to be perpendicular to the surface and is going to point perpendicular to the surface through the point of contact between the sphere and the surface. Whenever you are in contact with the surface, you also have friction. If we are rolling without slipping, that means that we have static friction because the velocity between the points on the surface and the surface itself should be zero. So that's going to be static friction there. And since if this were a block, let's say, on a frictionless surface rather than a sphere, the block would tend to want to roll downhill. And so we know that static friction would be acting uphill, acting against that direction of motion. So those are the forces associated with our point of contact with the surface there. That's the only point of contact. The other force that we have is due to the center of mass of the object, which should be at the geometric center, and the weight is going to act downwards at the center of mass of the object. Now that we have the forces, what we're going to do is look at our motion constraints. In this case, we are rolling without slipping, and so we have motion constraints associated with those. We've seen elsewhere that for the object to roll without slipping, there has to be a relationship between its center of mass and its rotational variables. We can also see here, if we're talking about the acceleration of the sphere's center of mass, we're talking about this quantity here, and that is going to be related to the angular acceleration of the object. So now we're going to look at Newton's laws. The first one to look at here is Newton's second law. These are vector quantities. And in practice, what we're going to have are a sum of the forces in the x direction is going to give us an acceleration in the x direction. Sum of the forces in the y direction is going to give us an acceleration in the y direction. If we lay out our axes like this, as we often do, then the center of mass of the sphere should accelerate down the ramp as the sphere rolls down the ramp. And so our acceleration in the y direction should be 0. The acceleration in the x direction, this is that acceleration of the center of mass that we're interested in. Looking at the forces that we have, similarly to what we've done with a free body diagram, we see that we have our normal force is already in the y direction, our force of friction is already in the x direction, and our weight is at an angle relative to these axes, but we can break our weight up into a y component and an x component as we've done before. So we can say here that a component of the weight, which is in the positive x direction, minus the force of friction, which is in the negative x direction, it's uphill. Those are the only two forces that are acting in the x direction. And so those have to give us our mass times our acceleration. And for simplicity here, I'm going to leave off my subscript, but let's remember that this a that we're finding here is the acceleration of the center of mass. I can also look in the y direction. I have a normal force that's acting up. I have a component of the weight that's acting down, and that should give me 0 because there's no acceleration in the y direction. Our sphere is rolling downhill. It's not going to be moving in the y direction. It's not coming off the incline there. Also notice, as we've seen before, if this is some angle theta, we're going to have an angle theta here as well inside of our system. So what we can say here is have our weight times sine of theta and our weight times cosine of theta. Also notice it's important to distinguish your w's here, because now when we have rotational variables, our w's and our omegas are going to look similar to one another. So we also need to consider our rotational motion, because this object is not just sliding; it is rolling without slipping. And honestly, here we don't know what this force of friction is. We know that static friction has a maximum amount, but friction here could be any value. It'll be whatever it needs to be so that the block rolls without slipping. And so what we're going to do is look at rotational motion and compare that. And we'll see that we'll be able to eliminate our force of friction there. So when we return to Newton's second law here, but in rotational form, our sum of our torques is I times alpha. Notice here that if we are accelerating downhill and we're rotating without slipping, alpha would have to be in this direction so that the sphere spins faster and faster in a clockwise direction so that it can roll downhill. So notice that's clockwise, that is the negative direction. If we look at what forces we have here, we're going to investigate the same forces that we looked at before, but in terms of looking at them in terms of torques. So what we're going to have here is a torque from the weight plus a torque from the normal force plus a torque from friction. And those torques are going to cause our angular acceleration. But let's look at these here. We can see that the normal force acts along a line. Normal force acts here at the interface between the sphere and the ramp, but the normal force is pointing vertically through the axis of rotation. So in that case, our phi value is going to be 180 degrees. Basically, we're going to have our center of our axis of rotation. We're going to have R pointing to that interface where the ramp is, and the normal force is pointing back at it. And so our phi value is going to be 180 when we say that the torque due to the normal force is R times F times sine of phi. Sine of 180 degrees is going to give us 0, and so the normal force is actually not going to contribute anything. If we do the same thing with the weight, here we have our sphere, there's our axis of rotation and the ramp. Our weight is acting right at the center of mass, which is also the axis of rotation. It would be at the geometric center of the sphere. For this case, r would equal 0, because r is the distance from the axis of rotation to the place where the force is being applied, and those are the same place. And so in that situation, if our torque is r times F times sine of phi, r is going to be 0 in that case because there's no torque being produced by the weight of the object. In the last torque that we should consider here is the force of static friction. The force of static friction is already perpendicular to the radial line. So our phi value in this case is 90 degrees. We're going to have r. We're going to have our torque from friction is going to be r times F times sine of phi. R is the distance from the axis of rotation to the point where the force is being applied. This distance right there is capital R, the radius of the sphere. F is the magnitude of the force. In this case, this is our force of static friction, and we just said that sine of phi is going to be sine of 90 degrees because we're already at a right angle there between the force of friction and the radial line. So this term right here is just going to be 1. Notice also that this torque here, this force of static friction, is going to cause clockwise motion, and so we need to give ourselves a negative sign there for our torque. We also said that the sum of our torques is I times alpha. Alpha, remember, is the magnitude, and we have to put a negative sign there because alpha is clockwise for us to roll without slipping. For what we can see here is that we can cancel out the negatives, and we can find our force of static friction is going to be I over R times alpha if we divide both sides by R. Also note that for a solid sphere, the moment of inertia is a fixed quantity. It is for any solid object. So for a solid sphere rotating about an axis that passes through the center of that solid sphere, our moment of inertia is going to be 2/5 mr squared. And so what we can do here is say this is 2 over 5 mr squared over r, and those will cancel as well. This is still times alpha. The other thing that we can do is say here's r times alpha, and we said up above r times alpha is a, the acceleration of the center of mass. Thus, we found that our force of static friction is 2 over 5 ma. We have an expression for this now that we can plug in. This quantity right here is our force of static friction that we've just substituted in. This is 1 ma. If I want to add 2/5 of an ma over, and I've already got 5/5 of an ma, when I add those together, I'm going to end up with 7/5 of an ma. I can also take the weight of the object and make that mg. And my m and m are going to cancel. And if I want to find a, the center of mass, I'm going to divide 5/7 there, or 7/5 there. I'm going to get 5/7 over here. I'm going to end up with my acceleration is going to be 5 over 7 times g sine theta, where g is our acceleration due to gravity, theta is our angle of incline of the ramp. In this case, is 25 degrees. And we get a value here, 2.96. It's an acceleration, so that should be meters per second squared. This is the acceleration of the center of mass of the sphere. I have 3 sig figs there, so I'm going to use 3 sig figs here. Our mass and our radius or diameter didn't end up mattering in this case, which is actually not surprising when you think about it, the same way that the acceleration of an object sliding down a ramp depended on the angle of incline of the ramp. Our acceleration here depends on the angle of incline as well. It also depends on the distribution of the mass of the object as it rolls down. There's a moment of inertia built into that term there, and so if we had a cylinder or a spherical shell or a hoop or something like that, the value would be a little bit different. But the idea of the mass and the radius are kind of built into that idea of the moment of inertia already. The other thing that we didn't account for is the force of friction. We eliminated force of friction, so we never actually needed to know it. But depending on what material the sphere is made out of, and also depending on the angle of incline, it would be easy to imagine this object skidding down the ramp and not actually rolling without slipping. And so we can figure out what the limit is for the coefficient of static friction if we assume that this here is our maximum. And then we also assume, if that is the maximum value of the static friction, then the maximum value of the static friction is mu s times the normal force. We actually know what the normal force is. We've seen this before. The normal force in this case is going to be mg cosine theta. We've seen that for an object on a incline before. If this happens to be a spherical object, it doesn't actually matter. The normal force is what it is. I'm also going to plug in for acceleration here. I'm going to plug in the old expression that we had. Notice here that m is going to cancel with m, g is going to cancel with g, 5 is going to cancel with 5, and I'm going to divide cosine over. When I divide cosine over, I'm going to end up with a tangent there. This term here is going to be a tangent of theta. And so our minimum coefficient of static friction for this to work would be 2 over 7 tangent of theta, which would be 2 over 7 tangent of 25 degrees, which in this case comes out to be 0.133, which is a pretty small value of the coefficient of friction, so it wouldn't be surprising at all for the actual coefficient of friction to be large enough for this sphere to actually roll down without slipping. But also notice that this dependence here on the angle of incline means that as the angle gets steeper and steeper, the coefficient of friction would have to be greater and greater for the object to roll without slipping. You could imagine if the ramp were almost vertical, the sphere wouldn't roll, but it would just kind of skid down the surface. So you can see why that behavior would be, what we would expect as well.